Hi, this is our Chapter 14 lecture on conjugated compounds and UV spectroscopy. We've mentioned conjugation a couple of times in the past, but we'll be talking about it in detail in this chapter anyway. It's when we have alternating single and double bonds within a molecule. So double, single, and right in order like that. And when we have that pattern of bonding, we end up with a compound that has different properties than similar non-conjugated compounds. So take a look at 1,3-butadiene. This is also a good reminder of how nomenclature of polyenes works, compounds with multiple double bonds in them. If I number this compound, doesn't matter which end I number this one from, but normally we'd number from the end closer to a double bond, right? 4 carbons in the backbone. Each double bond starts at carbon 1 and carbon 3, so it's 1,3-butadiene. If there were 3 double bonds, it would be a triene, it could be a tetraene, something like that. So if we would have had substituents on this could have easily been 2-methyl 1,3-butadiene or 2,3-dimethyl 1,3-butadiene or something like that. Put the numbers for the double bond locations right before the end of the name, just like that. So 1,3-butadiene is conjugated because it goes double, single, double. 1,4-pentadiene, right? 1, 2, 3, 4, 5 carbons in the chain, is not conjugated because it goes double, single, single, double. Okay? We've broken the conjugation by an extra single bond in between those double bonds there. It does not have alternating single and double bonds. So these compounds will have very different properties to them. The reactions they will undergo will give different regiochemistry anyway for some reactions. One reaction we'll talk about later in particular will only be able to occur with this conjugated diene and not with this non-conjugated diene. One way that properties of conjugated compounds can be measured, I suppose, is by measuring the heat given off, essentially using a calorimeter or something like that to measure heat given off when a compound is hydrogenated. So hydrogenation is just simple conversion of a double bond to a single bond with hydrogen and some catalyst like palladium, for instance. A double bond will release typically about 126 kilojoules per mole on average when it's hydrogenated. So it's not just the matter of breaking the double bond, it's breaking the double bond but also forming 2 new single bonds that makes this give off energy overall. Remember, anytime a bond itself is broken, energy is required, but we've formed 2 new single bonds to the hydrogens, in this case anyway. So it turns out with non-conjugated compounds, these values add up predictably. So if I have 2 isolated double bonds that are just in 2 different parts of the molecule, not linked by conjugation, the heat of hydrogenation, that's what this is called, ends up being almost exactly twice that of just 1 double bond, right? See, we would expect to have 2 of those 126s released. We actually get 253, which is just off by 1, so very close to prediction. For the non-conjugated compound, the conjugated compound, 1,3-butadiene, we would expect that same 252, but we actually get 236 back. So the compound is actually 16 kilojoules per mole more stable than we would expect, right? Being that we only get 236 out of it, the compound itself ends up being a good amount more stable. 16 kilojoules per mole is a significant amount. So these molecules are very similar. They both have 2 double bonds. The only difference is the conjugation. So conjugation itself lends an extra factor of stability to a molecule. It lowers the energy of a molecule. So, just so we're clear, heat of hydrogenation, this minus 236 comes about because the compound we started with was lower in energy. If we're going down to about the same point, just a regular alkane, the more stable compound has less of a distance to go down to become an alkane. The less stable compound gives off more energy to go down to be an alkane. So just so we're clear on that. But all we really need to know, the conjugated diene, 16 kilojoules per mole, about more stable than we would expect just for a regular compound with 2 double bonds. So we're going to talk about the molecular orbitals of conjugated compounds as one way of explaining why it is that they are more stable than we would expect. The reason for it is that if I have just some compound like ethylene, CC double bond, right, CH2 double bond, CH2. That double bond, you'll recall, is formed by one sigma bond that goes in between the carbons. I'll draw that in blue here. Okay. And also one pi bond that goes above and below the carbons. Okay? So what we're going to talk about here are the interactions of those p orbitals that overlap to form the pi bond. So if, say, I had just 2 regular isolated p orbitals, there would be a certain energy associated with those. Okay? If I bring them together and the lobes of those orbitals are aligned with each other, okay? Every p orbital has a lobe going one direction and a lobe going another direction. The electrons within them are in opposite phases when they're occupying either the top or the bottom parts of them. So you can just think of them as opposites. You'll see them colored red and blue or white and black or something like that. The specifics of what you call any one orbital doesn't matter. It just matters that the 2 lobes in one p orbital are opposite, and then the p orbitals next to each other can interact in one of 2 ways, right? There can be a bonding interaction where the lobes are aligned in their phases. Okay? There's constructive overlap between them. And sometimes it's helpful to think of electrons as moving like waves. If you have these that are overlapping constructively, the peaks and the valleys of each of those electrons are aligned with each other, so they reinforce each other that way. That's called a bonding interaction. Okay? Constructive positive overlap that reasonably occurs. So electrons will be able to be shared and delocalized across both of those orbitals when they're overlapping constructively. However, if we place those p orbitals next to each other where the phases are opposite each other, where I've got red one going down on one, red one going up on the other, we end up with an antibonding interaction. Antibonding, just like it sounds, is the complete opposite of bonding, where now these orbitals will actually be repelling each other, just like the opposite poles of a magnet, for instance. There will actually occur a node in between them. A node, I think we have that defined down here, a plane of 0 electron density between opposite phase orbitals. So I have these p orbitals that are misaligned. The node exists between them, so there is literally no electron density in this plane in between them. So they're not overlapping at all, they're not bonding, they're actually repelling each other. Let's look at what happened to the energy of these isolated p orbitals when they interacted in these 2 ways. The constructive bonding interaction lowered the energy because those electrons were able to be delocalized. Spreading them out makes them more stable. If you think of the wave nature of an electron, if I have a longer wavelength, that corresponds with a lower energy. Likewise, if we have an antibonding interaction between them, they're repelling each other, and it's actually less stable than those isolated orbitals were in the first place. So the original compound had 2 electrons in the pi system, 2 pi electrons. Each of these molecular orbitals will be able to hold 2 electrons at maximum. Okay? So the bonding orbital has a capacity of 2, the antibonding has a capacity of 2, but since I had 2 pi electrons to start with, we'll just have both of those electrons occupying the lower energy bonding molecular orbital. The antibonding molecular orbital will be unoccupied. One of these electrons would be able to be promoted up to this higher energy molecular orbital if the molecule were excited. We'll talk about that later with ultraviolet light. But in its ground state, this molecule has those 2 pi electrons occupying this constructive overlapping molecular orbital. That's why the pi bond actually occurs. Okay? This is our best description of a pi bond. Okay? We've talked about that before as the overlap of those p orbitals. That's just how it happens. Turns out the lowest energy molecular orbital will always have no nodes. Okay? It'll always be completely bonding interactions between all of them, and the highest energy molecular orbital will be only antibonding. When I only have 2 molecular orbitals, that's the only choices we have. I had 2 adjacent p orbitals here. That made 2 molecular orbitals. 3 adjacent p orbitals will make 3 molecular orbitals. Here, I can draw them for you. Let's use black so I can color them in. Okay. There's 3 adjacent p orbitals. They can overlap in any of actually 3 ways. Now, the lowest energy interaction will be all bonding. Here, I'll just use red to color them in. Okay, it's all bonding. In the middle, we need to have now 1 node, so that node will actually exist over top of the center p orbital there. So, got one going up on the left, one going down on the right. This is actually the same energy as the original isolated p orbitals. I have no constructive overlap that lowers the energy. I have no destructive overlap that raises the energy, so that's just the same. The highest energy will have nodes between every orbital. So we'll go up, then down, then up. That's the highest energy because they're all actually repelling each other, right? So remember what we called these. All overlapping is bonding. All repelling is anti-bonding. Where it's neither overlapping nor repelling, that's called non-bonding. And we only have one of those when there's an odd number of molecular orbitals. Okay? In this case, there were 3, so the middle one is going to be the same as the original. So that'll pretty much always occur if there's an odd number. The very middle one will be the same as the original one, not higher, not lower. We call that non-bonding because there's not actually bonding, there's not anti-bonding, it's just right in the middle. Even Steven, right? So let's go up to 4 carbons. 1,3-butadiene, molecule we started with this chapter. It contains 4 adjacent p orbitals, 1 on each of the carbons. Each of those p orbitals will contribute 1 electron to the pi system, or if you look at the original molecule, you could consider each of those double bonds that we had drawn in the original structure gives 2 electrons, right? So nonetheless, 4 pi electrons to the system. Because there are 4 isolated orbitals, we now have 4 molecular orbitals ranging in energy from lowest, which has no nodes, so it's all bonding, all the way up to the highest energy, which is all anti-bonding because there are nodes between all of them, right? Number of nodes always increases by 1, so 0, 1 node right in the middle between the 2 pairs, 2 nodes, okay, in the third one, so that I have up, down, down, up, for instance, as one of the colors, and then finally 3 nodes, up, down, up, down. So in butadiene, I have 2 bonding orbitals, I have 2 anti-bonding orbitals. This one is called bonding because there's more bonding than there is repelling. Okay? There are 2 bonding interactions and 1 repelling interaction. Here for anti-bonding, there is 2 repelling and 1 bonding. So if it's more repelling than overlapping, it's anti-bonding overall. Remember those original 4 electrons we talked about? Those 4 electrons, let's work out how those electrons will be occupying this molecule in its ground state. We'll start with first 2 electrons down in the lowest energy, okay? Then the next 2 in the second lowest. So we'll have the lower 2 orbitals being occupied. Remember, each orbital can hold 2 opposite spin electrons. The higher, okay, turns out these antibonding ones will be unoccupied. We have names for those. Specifically, the ones that will be important to us will be the lowest unoccupied, okay, and the highest occupied. Turns out those 2 molecular orbitals are very important for reactivity. That's where the promotion of electrons can happen in excited states. That's how molecules that are conjugated can absorb certain frequencies of light by promoting an electron up between there. Just for abbreviation, the lowest unoccupied molecular orbital is the LUMO, L-U-M-O, highest occupied HOMO, H-O-M-O. So being able to see in these electrostatic potential maps the actual bonding character that occurs in them is useful. In the conjugated compound, we notice that there's a good amount more electron density between those middle 2 carbons than there would be in a non-conjugated compound. See, the extra pi electron density is centered just over those double bonds, and that's it. Okay? Whereas the conjugated compound has some extra electron density between those center 2 carbons. That corresponds pretty directly with this lowest energy molecular orbital that has overlap between all 4 of those carbons. Now, there's less electron density in those middle 2 because the second molecular orbital is also occupied, where there's overlap on the left 2, overlap on the right 2, and a node between them. So in the actual molecule, it's going to be sort of an average for where these pi electrons are. There's going to be a lot of them between 1 and 2 and between 3 and 4. There's going to be maybe about half as much of that electron density between the center 2 carbons, but still some. Okay? If they were not conjugated, we would not have this all bonding interaction that has actual pi electron density between those center 2 carbons that way. This is actually a much more powerful method of imagining the behavior of conjugated compounds than just simply drawing double bond, single bond, double bond. Okay? Thinking of where those electrons are occupied as something like this, right? As the average of this, where they're overlapping on the end 2 ones quite a bit. There's some overlap in the middle, in the ground state anyway. That's a good way to think of it.